magnetic field of permanent dipole magnets. So the purpose of this lab was to compare the observed magnetic field of a bar magnet to the Biot-Savart law calculations for off and on axis magnetic fields obtained from a glow script model that we computed. And then the goals of this lab was to measure the magnetic field of a bar magnet using Tesla meter, which is a smartphone app, and to calculate the magnetic moment based off the data that we recorded, and to create a computational model to visualize the magnetic field of a dipole. The principles that we used in this lab is the Biot-Savart law for a single charge, as shown here, and the magnetic field of a bar magnet, as shown here. And here's a little visualization of what the magnetic field of a bar magnet looks like, starting at north and then going towards the south pole. So the procedure of this lab was to first determine the spot of the magnetic meter sensor on the phone, doing so by finding the maximum X component along with the minimum Y component, and then positioning the phone within the maximum Y component and the minimum X component. All of this while making sure that the phone is pointing in the true north direction in order to get the most possible accurate results. And then second was to record all the distances from the sensor to the bar magnet at every magnetic field in the X direction asked for. For example, Bx equals 20 mu teslas. And the final part was to measure the perpendicular distance from where B net equals 100. And doing so, Excel calculated the rest of our data for us. And here's all of my Excel data. The average perpendicular distance that I computed was 1.76, and then down there it displays all of my bx's and by's, and then here in the graph I got a linear line as expected with a k value of with an n value of 2.8367. And here's my work displayed for computing mu with the dipole moment. I ended up getting a value of 2.977. Observations found. So we found out that when the magnetic meter is far away from the magnet, it measures a near zero magnetic field in the X direction. And as the magnetic meter moves closer to the magnet, the measured X component of the magnetic field increases. Here's my code. So here we have the function that creates the magnetic field, and over here we created two arrows to represent the magnetic fields for the on axis, and then over here we have four arrows to display the magnetic field for the arrows perpendicular to the axis. And then here we have the code calculating dperp, and then down here we have the arrow for the magnetic field perpendicular to the axis. 45 degrees to the axis. And here's my model. Here's the 45-degree angle arrow. These the little blue ones are the ones perpendicular, and then these orange ones are the ones on the axis. And down here is all of my results from GlowScript. So the final results that I got. So these were calculated through Excel. So my B net ended up being this in the X component, this in the Y component, and then this is what I calculate through GlowScript, this in the X, this in the Y, and then I calculate percentage error to see how far off I was. So in the X component, I was off by 2.415%. In the Y component, I underestimated it by 0.89%, and then the Z component, of course, it was 0. Here it displays my linear equation that I got from Excel with an n value of 2.8367. So I had a percentage error of 5.44 since n was supposed to be 3 if this would have been done perfectly. Conclusion. So the charge of the magnetic field depends on the distance between the observation point and magnet. The farther away from the bar magnet means that the weaker the magnetic field gets, whereas when you're closer to the bar magnet, the stronger the magnetic field gets. And based off of my results, the X component of the magnetic field was just overestimated by 2.415%, whereas the Y component of the magnetic field was underestimated by 0.89%. These errors could be due to human rounding errors, the inaccuracy of the smartphone app, or interferences with the Tesla meter app readings such as a computer, or any other electronic device. follow-up questions. So what if I hadn't orientated my experiment to compensate for true north? So if I wouldn't have done that, my results would have been very inaccurate, as the Tesla meter app would have had very strange readings. So it would have been very different, and my values for mu, n, and k would have drastically been affected and been very off. And second question, what if I was to stick two identical magnets together and run the experiment again? So if I was to do this, the magnetic field would be twice as strong, and the direction of this magnetic field would be in the same direction. And that's it.